Hey everyone, welcome to this IBDP MAI HLSL course, and in this session we are going to talk about the geometric sequences and series, which is SL 1.3. We will see the geometrical sequences and series, their meanings, and how to apply these in the real life as well. Uses of formulas for the nth term, sum of first n terms of the geometric series, and also the use of sigma notation for the sum of geometric sequences. So we will look at all these things one by one. So let me tell you about the geometric series or sequences first. A sequence is said to be a geometric sequence if next term is given by multiplying the previous term by a fixed number. Like if I have a number, say a as my first term, and in order to get the next term, let's say I'm multiplying the previous by a number r. So that's the second term. This is a1. Now a2 is what? ar. Similarly, in order to get the next term, I need to multiply previous by same r number. Here, this R number is a fixed number, which we also call the common ratio. Why? Because if you take A3 by A2, you will get R. If you take A2 by A1, you get R. So in the same way, if you take any term, nth term, and divide it by its previous term, you will always end up getting the same number, which is the common ratio of the GP. So in this way, we can get the general term of the GP as well. Like if I want to find the 10th term. So A10, what is that? A times r raised to the power 9, right? From here you can see the pattern over here. So similarly, in order to get the nth term, what will be the final solution? A times r raised to the power 1 less, right? From the position. So A r raised to the n minus 1 gives me the general term. So remember this thing. Okay. That's the geometric sequence. For example, 1, 3. Now in order to get the next term, let's multiply it by 3 again. So 9, then again by 3, 27, 81, 243, and goes so on. If it is going so on, it means infinitely many terms are there. Or if I end it at 243, it means there are these 6 terms in that geometric sequence. We also call it geometric progression, GP. Okay. Now, series part. As you all know, in case of series, we have to add up all these n terms, right? So now you have seen how to find the general term, how to find the common ratio, okay, and the general term formula, which is this one. Now, the sum of n terms. For finding the sum of n terms means you want to add up all these. The formula is also given in your handbook. That is a times r 1 minus r raised to the power n over 1 minus r, this one, or a times r raised to the power n minus 1 upon r minus 1. Both are same. Okay. Both are same actually. If you take out minus sign common from this one, okay, so, and minus common from this part, you will, and cancel out those negative signs, you will get this one. So both are same thing. So this is the formula for n terms. Okay. Now, if there are infinitely many terms, what to do in that case? Right? I'll discuss that one also. The sum of infinite GP, and what is the condition under which we can find a convergent solution. Okay. Next. So let's discuss few questions on GP. It says for the following geometrical sequences, find the first term as well as the common ratios. So if you look at the first here, what is the first term? 5 is the first term. Yes. And what is the common ratio of this GP? Common ratio of the GP is given by dividing this by this. So 10 upon 5 is same as 20 by 10. It is a GP, right? So hence we can say the common ratio is nothing but 2. Similarly, for the second case, the first term is 24, right? And in order to get the common ratio, simply divide 12, right? 12 upon 24 will give you the common ratio. So 12 by 24, which is half, is the common ratio for this GP. Okay. You can also choose any term, divide it by the previous term, gives you the common ratio. Common ratio can be positive, negative, right? If common ratio is 0, it means you are multiplying each term by 0. So the entire sequence is 0 only. Okay. So we consider that common ratio is not 0, otherwise it's a constant sequence actually. Now, Next thing is this question, which is an application of geometric sequence. Let's see. It says a space probe in protective pod is released from an air spacecraft and falls out to the surface of the planet 20 meter below. On the impact with the surface of the planet, the pod bounces up, right? Now, engineers estimate the pod will bounce up to 65% of its previous height. Okay, so it's like this. Let's say this is the surface. Okay, a probe is dropped from here. It covers some distance over here. What is that? 20 meter, right? It is already given. Now, once it touches the surface, it bounces back, but it bounces up to only 65% of 20 meters. Okay, and reaches at this point and goes down one more time like this. Okay, goes up and covers the same distance again. Can you see that? When it comes down to the surface, it covers the same distance, that 65% of 20 this time. Let's say this is x unit. This height this time is x. Now, when it reaches the surface, it again bounces back, goes up to 65% of previous height. That was x. So it comes back and covers the same distance, 65% of x, then again goes up and so on, right? So in this process, can you see it covers this 20 meters only one time, and after this each distance is covered twice, this much and this much. Okay, so the diagram looks like this. Here the first height is 20 meter. Okay, and this second height, this one, is 65% of the 20, which gives me the second term. So what is that actually? That will be, the first term is 20, second term is 65 times 20 over 100, or you can say 0.65 times 20, right? So in this way it covers the same distance again, right? And for the next one, what will be the value? After that it covers 65% of this value. It means 0.65 whole squared. Can I write it 0.65 whole squared times 20 for this part? Yes, this height is 0.65 whole squared times 20. So can you see, I started with 20, then 0.65 times 20, then 0.65 whole squared times 20. Okay, it covers two times distance. So let me write two times also. Okay, so as you can see, in order to get the next term, I'm multiplying the previous term by 0.65, which represents it's a GP. It's a geometric sequence, right? So these are the distances, right? Now, it says in the first part, find to the nearest meter the total distance traveled by the pod at the moment of the fourth impact. So first impact is here. For the second impact, this plus this. For the third impact, this plus this. For the fourth impact, this plus this. So here we have to calculate this value. So what can I do? I can simply add up all these distances covered by the probe. Okay, so that will be my final distance for the fourth impact. Okay, so in order to calculate that, simply take 20 plus twice of 65% of 20 plus twice of 65% of previous plus twice 65% of previous. So in this way, I'm taking four terms, right? Now, either you can use your GDC to give you this value, or you can use the sum of first four terms of the GP, geometric sequence or geometric progression. Okay, so after simplifying it using the a times 1 minus r raised to the power n over 1 minus r, or simply using the GDC, I can get my answer as 73.885. In both the ways you will get the same. Okay, now next part says the physical condition. So you got the answer in this way. Okay, now the next part says the physical condition of the probe is measured in safety units. Each bounce costs the probe 2 safety units, and the probe begins with the 112 safety units. Now it says if the number of safety units falls below 84, the probe will fail. Now the question is, If the probe bounces exactly 13 times, so check whether probe will fail or not. So for that, what can I do? It always loses two safety units and the initial value is what? 112. So we are starting with 112. After every one bounce, it loses, after every impact, it loses two safety units. So let's calculate how many units left when it bounces 13 times. Okay. So for that, let's start with taking the first term as 100 and what? 12 minus 2. Why? Because at the first impact, it will lose 2 units. So that will be my first term. And what is the next term? Next time when it comes back, it again loses 2 units. So what is that? 110 minus 2, which is 108. Can you see? It was 110 earlier, then 108. Then what is the next? 106. What is that? It's a AP, arithmetic progression or arithmetic sequence, right? It is not GP this time. So yes, this time we are having an AP whose first term is 110 and the common difference is -2. So let's use that and calculate the 13th term. So it is given by un is given by u1 plus n minus 1 times d, where n is 13. The d value common difference is this -2 and the first term is 110. So when I use this, I got u13 as 86. After 13 bounces, we still have these 86 points. But it says if the value falls below 84, then it fails. But we are at 86, means it is not going to fail. Okay, and that's the answer for our question. Simply, we can say the probe is not predicted to fail because it hasn't reached to that 84 value, right? Or threshold value. Next, evaluate this summation from I equal to or r equals to 1 to 10 for 2 times 5 raised to the power r. So what it represents? Sigma means addition. So let's substitute. There are two ways to solve this problem. Either directly use GDC, right? You can go to function, menu, then calculus and sum. So GDC sum will give you directly this, where you can enter your r values starts from 1 to 10, right? Lower limit and upper limit, and enter the function 2 times 5 raised to the power r. That also gives you the answer. Or you can use you can form a GP using this. Let me show you. Put r is equal to 1, but I will get 2 times 5 to the power 1. Then summation means positive sign. That represents 2 times 5 second power plus 2 times 5 raised to the power 3. This summation represents the positive. This sigma represents means addition of the terms. So here I am adding the term after substituting those values, and this goes so on up to 2 times 5 raised to the power 10. Now can you see that it's a GP? In order to get the next term, you are multiplying the previous by 5. So here the first term or A1 is 2 times 5. The common ratio R is 5 only, and hence you can use the sum of first 10 terms of the GP, which is A1 means 10 times 5 raised to the power 10 minus 1 over 5 minus 1. Either simplify this in your GDC or directly use GDC to give you this value. And when I enter these points, I'll get answer as 2441460. This much. That's the answer. So either use GDC or use the geometric progression to calculate this sigma. Okay. Now, as I said, if we have infinitely many terms, then what will happen? How to find the sum? For example, if you have 1 plus 3 plus 9 plus 27 plus 81. Yes, it is GP, and let's say there are infinitely many terms. So terms are increasing. If you add up all the terms up to infinity, this sum is again going to be a divergent value. It is tending towards infinity, so it is divergent, right? For infinite terms, You will not get any answer, right? So there is a condition in order to get the sum convergent, means a value, the common ratio must lie between -1 to +1. Then only the sum will be divergent because the terms are getting smaller and smaller. For example, let's take with the 4 plus divided by 2. Okay, so 4 plus 2 plus 1 and again half of that, and then again half of that, then again half of that, and so on. So in this time, if you are adding these up to infinite terms, can you observe the number is becoming smaller and smaller and smaller, right? We started with 1.5 here, 1/4 0.25, 1 by 8 point 125, and so on, right? So number is becoming smaller and smaller, and as you can see, if we have infinitely many terms, the last term is almost zero, approaching towards zero. That's small. So yes, in this case, we can get a convergent sum for all these. And what we can do, how to get the answer? See, sum of n terms of formula was a times r raised to the n minus 1 upon r minus 1, or a times 1 minus r raised to the power n upon 1 minus r. So let's use those. So can I write it as a1 times 1 minus r tending towards infinity? Okay, the power n is tending towards infinity over 1 minus r. And if r is lying between -1 to +1, then we know that r raised to the infinity will tend towards 0. Okay, and hence we got our result, which is the sum of infinite terms of a GP is given by a1 over 1 minus r only. So this term gets becomes 0. So that's my answer for sum of infinite terms of a GP, but there is a condition that common ratio must lie between -1 to +1 only, right? Otherwise it will be divergent or oscillatory. Now, so here is the formula that you can always apply. Okay, let's solve a question here. It says find the sum of infinite terms: 45, -15, 5, -5 third, and so on. So the first term is what? This one is the u1. What is the common ratio this time? So let's find the common ratio, which is given by -15 over 45. -1 third. Yes, the common ratio lies between -1 to +1, and it is a GP, right? So in this geometric sequence, or this time it is a geometric series. So in this geometric series, sum is convergent. So let's find that value. So use the formula sum of infinite terms, which is u1 over 1 minus r. Use these and calculate the value. That comes out as 135 over 4. So that's my final answer. So in this way, you can find the sum of infinite terms of a geometric series. Okay. So in this session, we have covered everything required for the S1.3 topic. We started with general term formula, right? And saw that how to find the total number of terms or a given particular term, and sum of n terms, sum of infinitely many terms, right? And sigma representation, done. And also we covered a application of geometric series with that spacecraft problem. Okay, so that's it from my side for this session, and I'll see you all in the next session. Thank you for watching this. See you in the next part. Keep watching, keep learning.